Hello everyone, welcome back. In this video, I'm going to show an analysis of a summing op-amp or summing amplifier. So as like the circuit on the left here. All right. So it is an op-amp having a feedback resistor RF between V out and the inverting terminal, and then you have two resistors here, R1 and R2, that feeds off two input signals, if you like, V1 and V2. And as always, just a reminder of the assumptions that we have to make, or going to make, in terms of how we analyze an op-amp. The first one is, of course, that there are no currents going into a terminal because of the infinite input impedance inside the terminal, right? Inside the terminal, so no currents are going in. And the second one is that the node voltages V1 and V2 will track each other. So whatever V1 is, that's what V2 is going to be. Whatever V2 is, that's what V1 is going to be. All right. Okay, so let's have a look at the second assumption for this circuit. Since the non-inverting terminal is tied to ground, therefore the inverting terminal is also ground. So I'm going to label that as 0 volts. So on that node, that's this entire node here. That means the entire node there, right? You know, left of RF coming down, to the right of R1, to the right of R2, and then the wire that's going into the inverting terminal. So all of that is 0 volts. All right. Now currents. Let's label some currents. Well, you have, of course, let's say a feedback current IF, defined as going from right to left through RF. Okay. Now that current is going to flow, and then when it gets to this node, well, it's going to start to split. Well, based on the first assumption, none of that current will flow into the inverting terminal, so no current will flow through here. However, IF will be split between R1 and R2, so you're going to have a current. I'm going to call that I1. All right, so I'm going to call this current I1. So you're going to go through R1, and then I'm going to call the current that goes through R2 as, well, what else? I2, of course. All right. So that's my I2, and the one above it is I1. All right. So I1 is the portion of IF that will be split to go through R1, and I2 is the portion of IF that gets split into going through R2. All right. So what is this? I mean, this is basically just KCL, yeah, Kirchhoff's current law. All right, meaning that IF has to equal to I1 plus I2. All right. So in fact, that's the first equation that we will write. All right. So here we'll say based on KCL. All right. So that I can write I1 plus I2 is equal to IF. All right, so that's our first equation from the circuit, which we'll use a little bit later. Now, next we'll try and come up with expressions for each one of these. You know, what can we write about I1, what can we write about I2, and what can we write about IF? So let's do that. So if you look on the IF side, it's a current that flows through RF. So you can use Ohm's law to describe what IF is. That's what we're going to do next. So IF, so I'll say current through RF. All right, that's basically IF, right? So IF is equal to what? Well, Ohm's law, I equals V over R. The voltage would be, well, current is flowing from right to left, so therefore the voltage across RF is positive to the right. All right, and similarly for, let's just put down for everything else. So you have like the voltage across R1 will be positive to the right, and lastly the voltage across R2 will be positive to the right because the current I2 is flowing from right to left. All right, so we have the voltages as well. So for IF, right, is going to be VO. That's the output. All right, minus 0, all divided by RF. So that's our expression for the current through RF. Right. Next, let's have a look at the current across R1 and R2. Yeah, the current that is going through R1 and R2. So the voltage across R1 and the voltage across R2. So current through, I'm going to just make it a little bit shorter because I'm running out of space here. R1, all right, let's start with R1 first. All right, so basically we call that I1, all right, I1 is equal to, well, what is the voltage on top? Well, the voltage is right side minus the left side, which is, the right side is 0 volts, right? So therefore it's 0 minus V1, all divided by R1, okay? And similarly, current through R2 is just basically, we call it I2, is similarly 0 minus V2, all divided by R2. All right. So that's the expressions now that we have, the equations that we have based on KCL, based on Ohm's law, for all the things that we've labeled. So what we do now is to combine all these equations into our first KCL equation that we found. All right, so I'm going to put it down here. Okay. So that, if you like, becomes, okay, so it becomes what? Well, what is I1? I1 is just this, so I'm going to copy that. All right, so it's going to be, that's I1 plus I2, well, I2 is just this, is going to be equal to IF, right? So an IF is just this. All right, so that's the expression that we have. So now we just need to simplify it. So what can we do? Well, we can, because ultimately we want an expression of VO equals something, all right? So actually this is almost it. I mean, the only thing you have to do is just to move RF across to the other side, all right? And then you actually have an expression for VO. So I'm just going to switch these two equations around so that I have this equation on the left instead of the right, and these equations on these expressions being on the right instead of the left, all right? So therefore, I'm going to end up with an expression for VO is going to equal to, so all of these, which is negative V1 divided by R1 plus negative V2 divided by R2. Now, what I'm going to do also, I'm going to take that negative, okay, maybe I'll just do everything and I'll just show everything, okay? All right, so RF is the RF that was here, now it's moved across to the other side, so it becomes multiplied. So, and then inside the bracket, it will be V1 divided by R1, all right? And then, because this is a plus and minus, it becomes a minus V2 divided by R2, all right? All right, so next, I'm going to simplify it by getting that negative out. I'm going to take that negative out, all right? So then it becomes V1 plus V2 term. All right, so I'm going to do that next. So VO is going to equal to negative RF, all right, because I'm taking that negative from inside the bracket. So what's left inside the bracket would be just this expression, plus divided by R2, all right? Okay, so that's basically the expression for VO in terms of all the rest of the symbols. All right. Now, typically, what we can do is there are a few scenarios here. For example, all right, if we make all the variables, so sorry, all the resistance to be the same. All right. So that means if we make R1 equal to R2 equals to RF equals to R. All right, so that means everything becomes R. So then what's going to happen? Well, you're going to get an equation for VO, an expression for VO that is like this. So VO, therefore, is going to become, you still have the negative, all right? So R, all right, and then I can actually take the inside, the R1 and R2 now becomes R, right? So these two becomes R now. So I can take that out because they are the same, so I can factor it out. So it becomes 1 over R on the outside. And you multiply with it with RF, you're just going to end up RF over, sorry, not RF. You're just going to end up you just end up as R over R, sorry. Okay, so multiply by V1 plus V2. Which, of course, oh, sorry, I think that is entirely not correct. So I need to put a bracket around here. All right, and hopefully that will show it correctly. Yes. So it just simply means it is equal to V1 plus V2. All right, negative of V1 plus V2. All right, so that is a typical setup, if you like. If you set all the resistors to just a single identical value, then you're going to get an expression where VO is simply the negative of the sum of the voltages. So if you can imagine, let's say there are more of these, you know, R3, R4, and so on, and they're all at a value of R, then the output voltage is going to be the negative of the sum of everything, all right? So that's why it's called a summing OpAmp or a summing amplifier, okay? Another interesting expression for VO is when we make RF to be equals to R, but then for R1 we make it to be 2 times R. All right, so let's see what happens when we do that. So if RF is equal to R, all right, and R1 is equal to R2, and it's equals to 2R, 2 R's. 2 R's, that means 2 times R. All right, so then what's the expression we're going to get? Well, we're going to get a VO equals to, now based on the original equation here, right? So now, so RF equals to R, so that's negative R on the outside, all right? And then inside the bracket will be V1 over 2R, because now R1 and R2, they're both called 2R. So that's V1 divided by 2R plus V2 divided by 2R, all right? Okay, so so again, I can take the 1 over 2R from inside the bracket and take it out. So they're going to end up with a, okay, don't forget the bracket again. So I'm going to end up with a, like that, and then this is then multiplied by V1 plus V2. All right. Okay, so what does that become? Well, the R cancels out top and bottom, so you're going to get half. So you're going to get negative 1 over 2 multiplied by V1 plus V2, which is basically the average. All right, so the average of the 2 voltages. All right, so if you have more than 2 resistors here, if you keep on adding, you know, 1, 2, 3, 4, 5, and so on, and then for those values you make it to be n times R, you know, if there are n resistors, n times R, then you can create an averaging circuit. So this is an averaging circuit, right? The output voltage will be the average of the 2 inputs. So this is another interesting equation or setup that you can have. All right, so let me just label this. So maybe I'll call this summing unscale, right? Unscale summing. That means you're not scaling any input voltages. All right, and this one is a average average circuit. Yes. All right. Okay, so that's it. So thanks for watching this. Until the next time.